So I'm hoping that you've already tried this paper, but even if you haven't, try to watch the video actively. Don't just let it run. Pause it, try each question yourself, and then let it play to see how you did. Okay, so the first question is around solving equations, and it's the whole of the sort of first topic of this exam, a total of 32 marks, and that's as per what you can expect when you write. So the first one, we try to solve for x. X is in two different places, so what we're going to do is we're going to subtract cx from both sides. We're going to subtract d from both sides. What that does is it brings both the x's onto one side. Now, because x is in two places, the easiest thing to do now is to take x out as a common factor. So we get x into a minus c equals d minus b. The big advantage we've got now is that x is just in one place. X is being multiplied by a minus c, so we can get our final answer by dividing both sides by a minus c, and there's our answer for the first question. Okay, on to the next question. It's a quadratic equation. Remember, the standard thing with a quadratic equation is that we want 0 on the right-hand side. So we're going to add 6 to both sides of the equation. Now we're going to try and factorize this, okay? 2 factorizes nice and easily. It's what we call a prime number. The only way it can factorize is with 2 and 1. So we're going to write 2x in the one bracket and x in the other. Looking at the second sign tells us a little bit about what we can expect in terms of the signs. The only way we can get a positive product is for both our signs to be the same. When they're both the same, they will both be whatever that front one is. So in other words, they're both going to be positive signs now. So we can fill those in, a plus and a plus. Now we want factors of 6, and it's a little bit of trial and error, but either 6 and 1 or 2 and 3. But we find that if we put 2 there and 3 there, we end up with 4x and 3x. We've got our 7x. And now that bracket must be 0. So 2x plus 3 must be 0. So x must be negative 3 over 2. Just done that little step in our heads. Or x must be negative 2. Right, the next one is a quadratic inequality. So what we're going to do is, once again, we're going to get 0 on the right-hand side by adding 12 to both sides. Next up, we're going to divide every term by minus 1. Right, that'll change the signs of all those terms. Right, don't forget that we've also got to divide the 0 by minus 1, which is just 0. But don't forget also that when we multiply or divide by a negative, we must switch our inequality sign around. So there it is. It's now becoming a greater than or equal to. Next up, just as before with a quadratic equation, we're going to try and factorize. This one's even easier. This time we have an x and an x. Because the second sign is negative, our two signs are going to be different. We're going to have 1 plus and 1 minus. The only way you can get a negative product is to multiply a positive thing by a negative thing. Now we want factors of 12 that differ by 1x, and they are 4 and 3, and we want positive 1x. So there it is. Now we've got our sort of critical values of negative 4 and 3. Right, negative 4 and 3. And now many teachers will teach kind of you to draw a number line and look at the two factors on either side, on all those intervals. I like to actually visualize the graph, right? That function x squared plus x minus 12 is actually a parabola. And it's a happy, or what we call a concave up parabola, like a cup, okay? And those parabolas are positive outside of their roots. In other words, to the left of minus 4 and to the right of 3. Okay, so we're looking for them being positive. So bigger than or equal to 3 or less than or equal to minus 4, going to be our final answers. All right, and remember that we can include those values of negative 4 and 3. Right, the next one is an exponential, well, it's not an exponential equation, it's an equation that's going to require us to use some exponent laws. Right, what we're going to do first up is we're going to add 1 to both sides. Next up, we're going to divide both sides by 2. Remember, an equation is like a set of scales. We must do the same thing to both sides. Right, now everything in maths is connected to everything else, and here we're going to use an exponent idea, right, because we want to put an exponent there that will eliminate the exponent that's already there, and I unpack that a little bit. It also relies on some fraction stuff because we want to get down to x to the 1. we know that if we put a power outside that bracket on next to the 3/7, all right, that the two powers are going to multiply. So the question in our minds now is, what will multiply with 3/7 to give us 1? And as we know, the answer to that will be 7 over 3. The reason it will be 7 over 3 is because the 7s will divide out and the 3s will divide out, and we get x to the power of 1. That's absolutely fine, but just remember that whatever we do on the left-hand side, we must do on the right. So we're going to take our 21 over 2 and we're going to raise it to the power of 7 over 3. Let's bring up a calculator up to have a look at what that looks like. 21 over 2 to the 7 over 3. And yeah, here's a calculator coming in. There we go. And so we're going to type it exactly as it appears. 21 over 2 to the power of 7 over 3. Sorry, I've messed that up. So let's start again. Open brackets. Fraction 21 over 2 to the power of 7 over 3. Right, and the question paper said on the front cover that we must round to 1 decimal place. So there we have it, 241,4. Okay, right, let's look at the next question. The next question says, solve that. Now, very like the first question, we've got our variable in two different places. Right, so what we're going to do, we're going to take 3 to the x out as a common factor. And that's going to allow us to get x in just one place, which is surely going to be useful in terms of finding x. Right, so remember, when we multiply, we add our exponents, so we need a power -1 on that 3. Now what we're going to do is we're going to work out what's inside the bracket. All right, it's actually 1 plus a third. Okay, 1 plus a third, remember 1 is 3 over 3 as a fraction. So 1 plus a third is actually 4/3. Right, you could do that on a calculator, but I hope you wouldn't need to. Now what we're going to do is we're going to divide both sides by 4/3. When we divide by a fraction, it's the same as tipping and timesing. So it's actually 200 times by 3/4. And 200 times by 3/4, well, we can do that. That's 150. So what we've got now, we've got 3 to the x is 150. And when we have our variable in the exponent, we use logs. So we're going to write this in log form. X is log base 3 of 150. And our final answer, again, let's just bring up our calculator and take a look. Our final answer is going to be, so we seem to have put the calculator away. Let's see if we can find it. There it is. It's in fact going to be log base 3 of 150. And there we have it. About 4,6 to 1 decimal place. The next question involves completing the square, and this is a skill that you need to know. We're trying to solve for x. So the first thing, which I think is a reasonably obvious thing to do, is to add 3 to both sides. There's no x's in that term, so we're going to add 3 to both sides. Now the problem we've got is that x is in two different places. It's in the first term and in the second term. If we can write it in a completed square form, x goes to being in only one place, which will be helpful. Okay, let's see if we can do that. Right, so it's going to be x plus something. Now, let's just remind ourselves what happens when we square a binomial. Let's look at something like a plus b all squared. And let's just remember how that looks, okay? When we square a plus b, and I'm hoping you know this, we get a squared, sure. We also get b squared, but don't forget the outer and the inner terms, which actually are the product of those two things, doubled. So we actually get a squared plus 2ab plus b squared. I want us to focus on that 2 just for now, all right, because that 2 is highly significant. The number that I put in the bracket there is going to multiply with x and then double. So I want to end up with 4. So I mustn't put 4 in, because if I put 4 in, I'll end up with 8x. I must in fact put 2 in. So I need to halve that. Because it's going to be doubled, I'll halve it. It always makes sense. All right? If you square that out, you get x squared, you get 4x, but you also get 4 that wasn't there before. So what we've done, we've destroyed the balance by writing it like that, because we've added 4 to the left-hand side. The way we fix that is to add 4 to the right-hand side. We now have x plus 2 all squared equals 7. Next up, we're going to square root both sides, and we get, don't forget, the positive or the negative square root of 7. Sorry, that should be a 7. I see I wrote a 2. And then lastly, minus 2 plus or minus the square root of 7. Okay. All right. The next one is a log equation, and the way we're going to solve this is we're going to take it out of log form and put it back into exponent form. So the base there we've got is 2, so 2 to the minus 3 is 2x plus 1. Now that looks a whole lot more comfortable. We want to get x, we're going to subtract 1 from both sides. Notice here, the first thing we're doing is we're actually changing 2 to the minus 3 is to 1 over 2 cubed, or 1 over 8. Next up, we're going to subtract 1 from both sides, and we get negative 7 over 8. That's 2x, and then we need to divide both sides by 2, and we get negative 7 over 16. Remember, dividing by 2 is the same as multiplying by 1 over 2. It's the same as multiplying by a half, and we get negative 7 over 16. Negative 7 over 16, sorry. Right, the next one asks us to look at this equation, and this question is talking about the nature of the roots. So what we're going to need to do is we're going to need to work out our discriminant, delta. The formula for that is not given. It's b squared minus 4ac. However, it does appear inside the quadratic formula. It's the little piece inside the square root sign on the quadratic formula. So for this particular equation, delta is going to be 3 squared, which is 9, minus 4 lots of 2 times minus p. It's actually going to be 9 plus 8p. Delta is going to be 9 plus 8p. Now, for non-real roots, we want delta to be negative. All right? They're actually just asking for a single value. So any value of p that makes delta negative will work. For example, if p was, say, in fact, what I'm doing now is I'm just showing the boundary for p. So we know that 9 plus 8p must be negative, so 8p must be less than negative 9, and so in fact p can be any number less than negative 9 over 8. Okay, p less than negative 9 over 8. So for example, a number like negative 2 would suit our purposes perfectly. Or negative 3, there's any number of options, as long as it's less than negative 9 over 8. The next one now, we want a number which is going to give unequal rational roots. Now remember, we've worked out our discriminant to be 9 plus 8p. For unequal roots, we need that to be positive, but for rational roots, we actually need it to be a perfect square as well, right? So we're looking for a value of p that will make that thing a perfect square. Now, if we look at it, if p was 0, that would work quite nicely. But in fact, there are other options as well. If p is 2, we get 8 times 2, which is 16, plus 9, which is 25. All right. And that value will make delta bigger than 0. All right. But more importantly, as well as being bigger than 0 to give unequal roots, it will also give us a perfect square. And remember, a perfect square is what we need for rational roots. Okay. Right, the last, I think it's the last one, but we'll look now. We're matching discriminants to the x-intercepts of graphs of functions. Okay, and I'm afraid those x-intercepts in graph 2 have moved somewhat, but there we have it, all right? So remember that when delta is negative, we get no roots. Roots are x-intercepts. So if we look, graph 4 is the one that does not have any x-intercepts. It must be the one that has a delta value that's negative. All right, so it's actually delta 2. It's negative 3. Right, we get equal roots when delta is equal to 0. So delta equals 0 is actually delta 4. So that's that one where we just have equal roots, or one touching point, 2 equal roots. Now the next two both have unequal roots, and they have roots, so delta is bigger than 0 for both of them. The difference being, though, is that graph number 1 has got rational roots. roots that can be written as a ratio of whole numbers, roots that either end or repeat. Those roots, rational roots, occur when we have a perfect square for delta. So that'll be our delta 3, which is 25. And the last one, by process of elimination, must be our delta 1, which is 23. Remember that when delta is not a perfect square, we're going to get what we call irrational roots, roots that never end, never repeat, and can't be written as a ratio of two whole numbers. Okay, on to question 2, which is around patterns and sequences, or what we also call sequences and series. So the first one here talks about John starting his swimming training. He swims 4 lots of 25 meters. That's 100 meters. On the first day, he swims 100 meters. Right, 4 times 25, 100. The next day, he swims 1 additional lap. All right, so that's going to be 125 meters. On the next day, he swims another additional lap. That's going to be 150 meters. Now, at this stage, that's enough to realize that we've got an arithmetic sequence. Each term is telling us how far he swam on each day. Right, so on the 15th day, we want the 15th term. We're going to use our formula Tn as A plus N minus 1 lots of D. It gets provided to us, but it's certainly helpful to learn it to save yourself time. So T15 is going to be A, the first term, which is 100, plus 14, 15 minus 1, 14 lots of D, and D is 25, and there we have it. All right, and we get a final answer here. I think it might be 450 meters, but let's just have a look. Yeah, 450 meters. Right, the next one says, on which day will he have done a total distance of 15 kilometers? So now we talk about a total distance. Instead of talking about a sequence where the terms are separated by semicolons, we're now talking about a series where the terms are actually separated by addition signs. So 100 plus 125 plus 150. And we want to know how many terms we must add up to get 15 kilometers. Now be careful, 15 kilometers is actually 15,000 meters. So we need to change it to meters because the other terms are in meters. Right, so now this time we're going to use our sum formula. Sn, n over 2, 2 lots of A plus n minus 1 lots of D. Right, and we want an answer of 15,000. So we're going to put in what we know. We don't know n. We do know A is 100, so 2A will be 200. And we do know that D is 25. So n minus 1 lots of 25. Now we're going to solve for n here. Right, the simplest thing to do first up is to multiply both sides by 2. So we're going to get 30,000 on the right-hand side. And then we're going to multiply n into that bracket. So we're actually going to get 200n. And then we're going to get n multiplying by 25 times n, so 25n squared, minus 25 lots of n. Right, it still needs a little bit of tidying up, but it's essentially a quadratic equation. So we get 25n squared plus 175n minus 30,000 equals 0. Right, and now that is a quadratic equation which in fact doesn't factorize. We're going to use our quadratic formula. To save time, I'm not going to actually put those numbers in on my calculator. I'm just going to tell you that the answer comes out to, there are two answers. One of them is negative, which is clearly not the right answer for the number, for the day number. The other one is 31,3. Now, it's not possible to be 31,3 days. On the 31st, after 31 days, he would have swum less than 15,000. And after 32, he will have swum more than 15,000. So he swims 15,000 sometime on the 32nd day. So the answer is the 32nd day. Okay. Right, the next question is question 2.2. And it talks about a water-dependent frog which is trying to hop to a lake 2,7 meters away. Each time, the first jump that the frog makes is 40 centimeters. The next jump, because the frog's now tired, it can only jump 85% of what it jumped previously. 85% is 0.85. So 0.85 times 40. And on the next day, it can only jump 85% of that. So each day it's jumping less and less. I don't know if it's each day, not each day, each jump, sorry. So this one will be times 0.85 squared. And what we can see we've got here is a geometric sequence, right? And we've got a geometric sequence, and it turns out that R, our common ratio, is any term divided by the term before it. And we see that R is in fact, A is 40, but in fact R is 0.85. And we want the total distance, so we want to be adding up. So we've actually got a series here, 40 plus 40 plus 40 times 0.85 squared. The next one would be 40 times 0.85 cubed, and so it carries on. And the frog carries on jumping forever, theoretically. Right, now we know that we know what A is, but we also see that R is 0.85. That's what we are multiplying to get from one term to the next. If we take any two terms and we divide the term by the term before it, we get 0.85. That's our common ratio. Now that common ratio lies between -1 and 1, which is the conditions for what we call convergence. Convergence happens when our sum approaches a fixed number no matter how many terms we add up. Right? So we get a limit that occurs. Our formula is A over 1 minus R. So we get 40 over 1 minus 0.85. And we can bring up a calculator to work that out. Right, 40 over 1 minus 0.85. And we get an answer, and this is in centimeters, of 266.6. Right? In meters, we divide by 100, we get 2.67 meters. Actually 2.666 recurring. Okay, so 2.667 meters. Now the lake is 2.7 meters away. So no, the frog doesn't reach the lake. Okay, sadly for the frog, it doesn't reach the lake, and presumably it dies. Okay, right. The next question asks us to find K if those are 3 consecutive terms of an arithmetic sequence. Now remember, an arithmetic sequence has the property that any term minus the term before it will be the same value. Right? So in other words, if we take the second term minus the first term, notice I'm putting brackets in, that'll be the same as the third term minus the second term. The brackets are really important because the whole term needs to be subtracted. Okay, now from here it's just some algebra. I'm just going to tidy that up. It's 4k minus 6. That's a little bit better. Right, now we're going to subtract and subtract, and we're going to see what we get. Remember, we're trying to solve for k. We've got an equation, so it's just a question of tidying this up. Minus 3k minus 2, and on the right-hand side, k minus 2 minus 4k plus 6, because it's subtracting a negative, which is the same as adding. Right. Now let's just tidy it up some more. We collect the like terms. We get k minus 8 on the left, and we get negative 3k plus 4 on the right. Let's add 3k to both sides. Remember, this is like a set of balance, like a set of scales. All right, so 4k minus 8 is in fact 4. Let's add 8 to both sides. So we in fact get 4k equals 12. Let's divide both sides by 4 and we get k equals 3. Right, and that's the answer. If in an exam situation you've got time, just for confidence sake, just to boost your confidence, to show that we've got it right, let's just see. The first term, if k is 3, the first term would be 11. The second term would be, in fact, 12 minus 6, it would be 6. And the third term would be negative 1. Sorry, the second term is actually 5. So it's decreasing by 6 each time, and our answer is definitely correct. Right, the next question asks around convergence, and we've already spoken about that on the frog question. But geometric series converge when R is between -1 and 1. That's when convergence happens. okay, not including minus 1 and 1. Right, now in this case our r, if we take any term and divide by the term before, is negative k plus 3. So we want that r value of negative k plus 3 to lie between 1 and minus 1, or minus 1 and 1. Now we're going to solve this. This works exactly like an equation, but we've got three sides. We're subtracting 3 from the left, the middle, and the right. Now we're going to multiply or divide both sides, in fact all three sides, by negative 1, because we don't want negative k, we want k. All right, so we get k there, we get 2 there, we get 4 there, but remember that when we multiply or divide by negative, we must change our inequality signs around. So there's the answer. A slightly neater version of it is to write the numbers, write the smaller number on the left. K lies between 2 and 4. Right, other way we could write that is k is an element of 2, 4, with round brackets because we are not including the 2 and the 4. Right, you don't have to write both, just two different formats for writing that answer. Okay, the next one gives us two bits of information and asks us to write down the first three terms. Now the things that we would need to know for an arithmetic sequence to write down the first three terms are what does it start with and how much is it growing by? What is A and what is D? Typically in maths, when we are required to find two variables, we will need two equations. And we can set up two equations here. Firstly, the fact that T7 is 13, all right, we can use our formula for Tn. Tn is A plus n minus 1 lots of D. So if T7 is 13, that means that 13 is A plus 6, 7 minus 1, 6 lots of D. So it's actually the sixth term, so 5 lots of D. All right, and now the sum of some terms is 120. Here's the sum formula. Sn is n over 2, 2 lots of A plus n minus 1 lots of D. Now we know that the sum of 10 terms is 120. So we're going to put 120 over there, and that's going to be 10 over 2, which is 5. 2 lots of A, I don't know A, plus 10 minus 1, 9 lots of D. Right, and I've got two equations. That's equation number 2. Each of them has two variables in. And what we're going to do now is we're going to solve them simultaneously. From one of the equations, the equation number 1, we're going to get a variable on its own. It's easiest to get A on its own by subtracting 5D from both sides. So A is 13 minus 5D. What we're now going to do, we're going to write out the other equation. But instead of writing, what we're doing first is we're dividing both sides by 5 just to tidy it up a little bit. Okay, just to make it a bit simpler. So now, instead of writing A, I'm going to write what A is equal to in that second equation. A is 13 plus 5D. I've highlighted it yellow. I've also highlighted the A yellow. All right, and so now we're going to write down that second equation. 24 is 2 lots of A, all right, plus 9D. Now remember, A is actually 13 minus 5D. Lo and behold, what we have now is we have just one variable, just D. So we're going to simplify this a little bit. So that's minus 10D, and that's plus 9D. And we're solving here for D. All right, so we get negative 2 is in fact equal to negative D. All right, we can divide both sides by negative 1, or times by negative 1 in fact, and we get that D is equal to 2. Right, now we're going to find an equation where we've got A equal to, and that's that one just higher up there. We know that A is 13 minus 5D. So if D is 2, 13 minus 5 lots of 2, 13 minus 10, A is 3. We may think we're finished, but we're not. Let's just remind ourselves, it asked for the first three terms. So if A is 3, that's the first term. If D is 2, the next term is 5, and the next term is 7. And there's the answer to that question. Right, the last question I think in this topic is to find the nth term of a sequence. Now if we look at this, there's not a constant difference, nor is there a constant ratio. So it's not arithmetic and it's not geometric. So what we're going to do is we're going to start off by writing down the first differences. Okay, so the first differences between the terms. and they are 2, and then 4, and then 6, and then 8. Right, those are our first differences. They're not constant, so it's not an arithmetic sequence. Now we're going to look at the second differences, which is the differences between the first differences. All right, so 4 minus 2 gives us 2. 6 minus 4 gives us 2. 8 minus 6 gives us 2. Because we've got a constant second difference, we know that we are dealing with a quadratic sequence. And we get given this little formula, Tn is an squared plus bn plus c. It's not a particularly helpful formula, and there's some other formulas now that we don't get given that we need to be mindful of. We know, and I hope we know, that a is our second difference divided by 2. So in this particular case, a is going to be 2 divided by 2, all right, or just 1. Another formula that we're not provided is that 3a plus b is the first term of the first differences. So 3a plus b is T1 of the first differences. Now if we go and look at our sequence of first differences, our first term there was 2. Right, so 3, we also know that a is 1, so 3 lots of 1 plus b is in fact 2, and that 2, right, I'm going to highlight it, is just that 2, which is the first term of the first differences. Okay, so didn't get the highlighter. There's the highlighter. Right, there we go. Now, there's only one variable left in there. If I subtract 3 from both sides, I get b equals minus 1. Right, the next one, and it comes straight out of the little formula there, is that T1 is a plus b plus c. So in fact, a plus b plus c is the first term of the entire sequence, of the original sequence. T1 of the original sequence. Now, this happens to be 2 again. That's just a coincidence that it's 2 on both occasions. Just going to make sure we realize which 2 we're talking about. We're talking about that 2 right at the top in the question. We're going to just highlight that. There we go. That 2 and that 2 there. Right. So, in fact, a, which we know is 2, so we know a is 1. We know that b is minus 1. So plus c, and we know that that is 2, the first term of the original sequence. There's only one variable left in there, and that's c. So we get a final answer of 1n squared minus n plus 2, and there it is. Okay, what I like to do is I like to just test that formula, just to check that I'm right. So for example, if n was 3, we get 3 squared minus 3 plus 2, we actually get 8. According to our formula, T3 is 8. 9 minus 3 plus 2, 6 plus 2 is 8. Right, let's just scroll back up and just check. Notice this is not required. This is just me checking that I've got it correct. Okay, and that brings us to the end of that section. And now we are on to our next topic, which is functions and graphs. Quite a big topic in your upcoming exam. The first question here asks for the domain of the function of f. Now, it's important to look carefully at that. There's two things at play there. One is the square root. We cannot square root a negative number, all right? So we can't have a negative inside there. We also can't have a 1 in the x on the denominator, because that would give us a 0 on the denominator. So x is not equal to 1 is the first thing. Now let's look. We need the stuff inside the root sign, the negative x squared plus 9. We need that to be bigger than or equal to 0. This is a quadratic inequality. We're going to multiply through by negative 1. So x squared minus 9. 0 times negative 1 is 0, but we must switch the inequality sign around. Now we're going to factor that, all right? And it factorizes easily. It's a difference of squares, x minus 3, x plus 3. And this, again, the critical values are negative 3 and 3. And I'm looking at a happy parabola, a concave up parabola like a cup. But this time, unlike the previous quadratic inequality, I want to know where is it below the axis? Where is it less than or equal to 0? Right? And it's less than or equal to 0, okay, in between minus 3 and 3. Okay, so we're looking for less than, in between, minus 3 and 3. So our final answer to this question is x is an element of minus 3 to 3. We can include those, so we're going to put square brackets on. But don't forget that x cannot equal 1 either. 1 lies inside there, but 1 is a problem because it makes the denominator 0. And remember, we can't divide by 0. Right, when we have 0 underneath, it's undefined. Right, the range of g, that's a much easier question. That's just an exponential graph, right, that's been dropped down by 1. Okay, so it's an increasing exponential graph, but it's been dropped down by 1. All right, and it has, in fact, an asymptote, a horizontal asymptote at y equals minus 1. And so, in fact, the range is y greater than minus 1. Remember that the graph doesn't touch the asymptote. It's strictly above minus 1. Okay, right. The next one is finding the inverse of a function. All right, and the function in question is actually function y equals 3 to the x plus 2 minus 1. All right. So first thing we're going to do is we're going to swap x's and y's around. I like to just make up an x value and work out the y value whenever I do the inverse of a function. So for example, if x was 1, all right, the y value would be 3 to the 3, 1 plus 2, which is 27, minus 1, which is 26. I want to make sure at the end that what I come up with as my inverse will generate 1 when I put 26 in. X's and y's swap around when we find an inverse function. So what I'm going to do now is I'm going to swap x and y around. So x equals 3 to the y plus 2 minus 1. And now I'm going to try and get my equation in the form of y equals. I'm going to solve for y. I'm going to make y the subject of the formula. Let's add 1 to both sides. And I get x equals 3 to the y plus 2. I now need to solve for a variable in the exponent, so I'm going to use logs. All right, y plus 2 will actually be equal to log base 3 of x plus 1. Just careful, it's all of that, log base 3 x plus 1, so I need brackets. Last thing I'm going to do is I'm going to subtract 2 from both sides. So my answer is log base 3 x plus 1 minus 2. And I'm going to just write now g inverse of x, not f, sorry. G inverse of x. So, because that's the form that they've asked me to write it in. Last thing I'm going to do, just for my own satisfaction, is I'm going to check if I put 26 in there for x, I get 27 inside the bracket. Log base 3 of 27 is 3. 3 take away 2 is 1. And lo and behold, I get 1 out. That's very convincing that I have got this question correct. The next question asks about a parabola, and it says, and it's actually a concave down parabola, that's what we call a SAD parabola, although concave down is more mathematically correct. And it says, is the inverse of that thing a function? Now, the important thing to notice is that although that graph passes a vertical line test, it doesn't pass a horizontal line test. A horizontal line hits the graph at more than one point at a time, right? So we say that h is in fact many to 1, all right? It's still a function, but it's many to 1, right? Now, when we find an inverse, those things swap around. So in other words, instead of being many to 1, it becomes 1 to many. And 1 to many will not be a function. So h inverse will be 1 to many. So the answer is no, it's not a function. Just to unpack this question a little bit more, or just this idea a little bit more, if we've got a parabola, for example, y equals x squared plus 1, it's just a concave up parabola that's been shifted up 1, y-intercept of 1 like that, looks something like that. That is, as we said, many to 1. The inverse of that function, all right, is a reflection around the line y equals x, always. An inverse is always a reflection around the line y equals x. The inverse is actually a kind of a parabola lying sideways like that. And we can see that the inverse is not a function. The inverse fails a vertical line test. Right. What we could do, we could restrict the domain of the original function. So in other words, the y equals x squared plus 1. We could just take half the parabola. We could say, let's not let x be negative. Let's just take x bigger than or equal to 0. And if we did that, then we would only get half of the inverse out like that. And in fact, we now would have a situation where the inverse is a function. Right? The only one you need to be able to do this for is a parabola. Right? Your other functions, for example, your exponential, your hyperbola, your log graph, those are all one-to-one functions. So one-to-one, the inverse will also be a function. Right, the next question says, and this is a little bit tricky, but it says show that J is a hyperbola. Now J is actually defined as follows: 2x plus 3 over x plus 1. Now it doesn't really look anything like a hyperbola, but there's a little trick here. If we could write the top as 2 lots of x plus 1, right, and the reason I'm choosing x plus 1 is because I want it to be able to divide with the stuff on the bottom, right? So look what I'm doing. I'm writing an x plus 1 there. Now if we multiply that out on the numerator, we've got 2x plus 2. So that's not correct because it was 2x plus 3. So we're going to add 1 at the back. So 2x plus 1 plus 1. Right, now if we separate that fraction, and remember we can separate fractions at the top. So I'm going to write that as 2x plus 1 over x plus 1 plus 1 over x plus 1. Now that first term actually is just 2. So actually I just get 1 over x plus 1 plus 2. And that is quite obviously a hyperbola. All right, so it's just a little trick. It's an algebraic manipulation to convert that thing which didn't look like a hyperbola to show that it in fact is a hyperbola. All right. Now the x asymptote of that is x equals minus 1, and the y asymptote is y equals 2. All right, fairly tricky that. If you haven't seen it before, hopefully if it comes up, you'll remember that little trick. The next question says, give in standard form the equation which results when we move that graph 3 units to the left and 1 unit down. Now remember the way in which we're going to move a graph left, all right, we've got our function, there it is, negative x squared plus 3x minus 5. Now the way in which we're going to move it 3 units to the left is we are going to add 3 to every x value. So in other words, we're going to work out h of x plus 3, and then we are going to minus 1 at the back, and the minusing 1 will drop that graph 1 unit down. But notice h of x plus 3 means replace all the x's with x plus 3. All right, and then there's the minus 1 at the back, and there we have it. So instead of x, we have x plus 3. Instead of x, there we have x plus 3. And that's our answer, but they did want it in standard form, so we're going to need to multiply this out and get rid of the brackets and collect the like terms. Squaring a binomial is something we do often. X squared plus 2 lots of 3x is 6x plus 9, plus 3x plus 9, minus 5, minus 1, sorry, plus 3x plus 9, minus 5, minus 1, minus 6, and now we can get our final answer, negative x squared. We actually get minus 6x plus 9, sorry, minus 6x minus 9. All right, what happens here is that the negative 9 and the 9s cancel. We get our final answer of negative x squared minus 3x minus 6. Okay, the next question asks us to find the equations of 2 different functions. The first one is a hyperbola, and we need to recognize it, and we need to know that the sort of vanilla or parent function for a hyperbola is k over x. However, this one has been moved. We can tell that it's been moved by looking at the asymptotes. The asymptotes are normally on the axis, on the x and y axes. All right, this one has been moved 2 to the left. To move it 2 to the left, we add 2 to every x. There's only one x, but we add 2 to it. And to move it 3 down, we subtract 3 at the back. Every single hyperbola with those asymptotes can be written in that form. Now we want the specific one that's going to go through that point to -1. So what we do is we substitute that point to -1 in, remembering that 2 is x and -1 is y. So -1 equals k over 2 plus 2 minus 3. And now we're just going to solve for k. So we add 3 to both sides. We get k over 4 is 2. So k is 8. And then our final answer, y equals 8 over x plus 2 minus 3. Okay, the next one is in fact an exponential graph. And the sort of base or parent function for that is ab to the x. You need to learn that. All right. And now what we're going to do is we've realized that the asymptote has moved up. So the graph has moved up by 1. So this one's ab to the x plus 1. There are now two things that we need to find, a and b. And we've got 2 points. However, it is important that we use the y-intercept first. All right. You'll notice that if we use the y-intercept, 0, -2, -2 being y, we still apparently have 2 variables. But the b is being raised to the power of 0, and b to the power of 0 is just 1. If we use the other point first, we would have a problem because we'd still have 2 variables. Okay, so put the y-intercept in first, and now we get -2 equals a plus 1. Subtracting 1 from both sides, we actually get a is -3. So now our equation is -3 b to the x plus 1. And the last thing we're going to do is, in fact, put in the other point, all right, -1/2 for y and 1 for x. And so we get -1/2 is that. Subtract 1 from both sides, we get -3 over 2 equals -3b. And dividing both sides by -3, we get b is 1/2. B is positive 1/2. So our final answer, all right, is y equals -3 times 1/2 to the x plus 1. Okay, just to make it clear what's actually kind of happened here, remember that 1/2 to the x is actually a decreasing exponential function because the base is less than 1. The -3 causes it to be reflected and actually made slightly steeper like that. And then the plus 1 actually picks it up. And so that's the basic shape. If you scroll back to the question, that's the basic shape that we had with the asymptote above the x-axis. Okay, the next question is this one. We've got 2 functions, a parabola, a concave down parabola, and a straight line. And the first question asks us to find out where they intersect, all right? Now, they will intersect at the points where their y values are equal, and in fact, their x values are equal. So we're literally just going to put the 2 equations equal to one another. -x squared minus x plus 6 equals -2x. All right. And so we're going to just solve this. Let's add 2x to both sides. We get that. Let's divide everything through by -1. So we get x squared minus x minus 6 equals 0. We've also divided 0 by -1. This factorizes quite easily. Remember, we're going to look at the second sign. All right, it's negative, so these must be different. 1 positive and 1 negative. Factors of 6 that differ by 1. And we actually want a negative result, so we put the bigger one next to the negative sign. And there it is. So our x values, in fact, are -2 or 3. Each of those we can put into either function. The simpler function is a straight line. So -2 times -2 is actually 4, positive 4. But 3 times -2 is actually -6. All right. So those are the y values. It's a really good idea always to write them as points, in fact. Okay. So we've got a point C, which is that one over there, -2, 4. And a point D, which is down there, 3, -6. -2, 4, and D, 3, 6. Then it says hence. And now the word hence, it's an English word, it's rather an old-fashioned word, but it means using what you've just done. Now, give the value of x for which f of x is bigger than or equal to g of x. When we talk about f of x, we actually talk about the y value of f, and when we talk about g of x, we talk about the y value of g. Where is the y value bigger than the y value? Now, remember that a y value that's bigger actually means above. What we're asking for here is really, where is f above, higher up than g? Where is f above g? So if we go and look at the picture here, well, we can see that the parabola f is above the straight line from -2 up to 3. So that's going to be our answer, all right? From -2 up to 3. Notice it actually says above or equal to. So in other words, we can include -2 and 3. If we chose to write it, and we don't need to, but if we chose to write it with interval notation, we would use square brackets. Square brackets because we can include those endpoints. All right, the next question talks about a vertical line. Now, the crucial thing with a vertical line is that we need to know how to work out the length of a vertical line. Right, the first thing though, before we even get there, is understanding that any single point that lies on that parabola has a relationship that is equal to the equation of the parabola. Now I'm going to explain what I mean by that. If, for example, the x value of that point is x, then the y value is negative x squared minus x plus 6. Every single point on the parabola has that relationship. In other words, if the x value is d, it would be negative d squared minus d plus 6. If the x value was 8, it would be negative 8 squared minus 8 plus 6. That's a really, really important concept, and we're going to come across it again a little bit later, maybe even twice more in the calculus. All right. This one, because it lies on the line negative 2x, the y value will be negative 2x when the x value is x. All right. Now, the distance or the length of a straight line is a vertical line, rather, is just the bigger y value minus the smaller y value. For example, suppose over here that we had, suppose a y value sorry, we're not getting there yet. We're going to just look at the length of AB. So we're going to go the bigger y value minus the smaller y value. So yeah, I think, suppose that was 5 and that was negative 2. That length of that line would actually be 7. 5 subtract negative 2, which would give us 7. Okay, so we're just going to take the y values and subtract them because it's a vertical line. So negative x squared minus x plus 6 minus 2x. And what we get is we get negative x squared minus x minus 2x, so it's plus 2x, so it's plus x, and then plus 6. Now that is the length of that line. What we want to do now is we want to work out where is that, because that in itself is a graph, right? And that's actually a concave down or sad parabola with a maximum value. Where is that value? All right, what's the maximum value there? There's a couple of ways we can do this. We could use our negative b over 2a to find the turning point of that parabola. I'm going to complete the square. I'm factoring out the negative, and I get like that. Now inside, now this is the completing the square part. Remember, I need to halve the number of x's, and I've got one x, so it's going to be x minus a half. All right. And when I square that out, I get x squared minus x, which is great. But I also get a plus a quarter, which was not there. So I need to subtract a quarter. Now, the reason I'm subtracting a quarter is I'm on the same side of the equal sign. Right? Previously, when I solved an equation, I was on the opposite side, so I had to add that number. Right. There it is. That's an expression for the length. And that length, the furthest those graphs are ever apart, is actually 6 1/4. Okay, we can see that because when we square something, it's always negative, right? Unless we put a half in, right, that's when we'll get 0. Sorry, when we square something, it's always positive. When we put a negative in front of it, it's always negative. And so the maximum length is actually 6 1/4. Okay, and that happens when x is a half. Right, now it says, and it's the same word again, it says, hence, using what we've just done, now, give the values of k if that equation, f of x plus k equals g of x, has no real roots. Now, when we put f of x equal to g of x, in other words, if k wasn't there, we'd be talking about where those graphs intersect. That plus k is going to shift f up or down vertically, right? Because it's f of x plus k. The plus k is outside the bracket. That's going to shift the graph of f up or down. A vertical shift. It will shift it up if k is positive and down if k is negative. So let's just go now and just have a look at the picture. At the moment, as the graphs are, f of x equals g of x, there are solutions. We found them already in part 1, okay, that the graphs do cut. But if we were to drop graph f down, if we were to lower it, there would come a point where it wouldn't touch graph g at all. And in fact, if we load it, remember the furthest apart that they are is 6 1/4. If we load it exactly 6 1/4, it might look something like that, where it just touches the graph of g, and there would be one point of intersection. And if we load it more than 6 1/4, there would be no points of intersection. Now remember, to lower it, we want a negative value. So in fact, we want to be more negative than 6 1/4. Right, and that's the solution to that. Now we're going to just have a look at a little diagram of that. There's the picture as it was in the question. And now I can adjust my k value. Notice if I make k positive, the graph lifts up. I'm adding k to f of x. Notice if I start dropping down, and we can see the k value there, it's getting lower and lower. When I get to negative 6 1/4, all right, there it is, negative 6 1/4, those graphs are just touching. If I go slightly smaller, they actually will come to a point where they, in fact, are missing one another. It might look like they're touching, but in fact, if I zoom right in, we'll see that they actually are missing each other at that point. Okay, so we need to drop it by more than 6 1/4. Okay, hope that's been useful. We're going to come back to that sketch shortly, or it's a slightly different one. So I'm just putting that back to 0. Right, let's go now and look at the last question here, which says determine the values of t if f of x plus t equals 0 has two roots of the same sign. Now this is a left-right shift, not an up-down shift. This is a left-right shift. And that's because the t is inside the bracket. Okay, so if we go back to the picture, at the moment, the function f has got two roots, negative 3 and 2. Let's just draw it over here where there's a little bit less kind of going on, just so we can see. We've got a parabola. It's got two roots, one of them at negative 3, the other one at 2. One of them is negative, one of them is positive. Now the question is, I'm going to move this graph left or right, and I want the roots to be of the same sign. Now I'm hoping that what you can see is that if I move it left, by more than 2, then both of the roots will be negative. Okay, if I move that whole picture, that whole graph left by more than 2, both of the roots will be negative. Now remember, to move it left, I actually need to add an amount. So I must add more than 2. Alternatively, or Norma, I can move it right by more than 3. Now remember, to move it right, I actually need to be subtracting. So I would want things like f of x minus 4, f of x minus 5, even f of x minus 3, 1. All right? I need values that are more negative than negative 3. In other words, t must be less than negative 3. Okay, t less than negative 3 will move the graph more than 3 to the right. Let's go back to that sketch and just have a look at how that actually plays out. So what we've got here now, sorry, just waiting for it to come up. There it is. Okay, what we've got here now, as I make t bigger, you'll see the graph, the orange graph, moving to the left. All right, and you'll see that once I get to 2, I've got a negative root and a root of 0. As soon as I go more than 2 to the left, both of my roots are negative. Okay, let's go the other way, right, from 0. If I make t negative, it actually moves the graph to the right. This sort of works opposite to what you might expect, but it does make sense if you stop and think about it. And when we've moved it 3 to the right, I've got one positive root and one root of 0. And if I move it more than 3 to the right, I've got two positive roots. So two roots of the same sign. Okay, I hope that sketch was kind of helpful in reinforcing your understanding of this. Okay, the next question I think we're going on to now, let's just take a look. All right, just remember that that's a left, that's an up-down shift, and the one inside the bracket is a left-right shift. Okay. Right, we're now on to our last question, which is question 4, and it is actually the most marks, and it's all around calculus. Okay, and what the first thing we're going to do is we're going to find, by first principles, we're going to find the derivative of negative 2x squared plus 3x. Right, we get provided with this formula. The derivative's limit is h tends to 0 of f of x plus h minus f of x over h. And just a quick reminder of what's actually happening here, okay? What we've got is we've got a piece of function. We don't necessarily know what it looks like. In fact, yeah, I'm just going to draw it's the model of what's happening here. And we've got 2 points on the curve. We've got a point x, and as I said to you earlier, because that point is on the curve of f, the y value is actually f of x. And then we've got a point a little bit further along, and that's h units further along at x plus h. And because it's on the curve of f, its y value is f of x plus h. Okay, now what we're going to do is we're going to use those 2 points to find the gradient. We're finding what we call an average gradient. And in fact, we're finding the gradient of a straight line joining those 2 points. All right, so let's just see if we can draw in a straight line there. It's hard to see. That black line's actually a curve, and the green line is hopefully looking like a straight line. All right. Now, if we find the gradient using those 2 points, we get exactly what's in that equation, because it's the y values, f of x plus h minus f of x, and the x values is actually, the difference between them is just h. So that's where that formula comes from. Now, we obviously want h to be tiny in order to get the most accurate answer for the gradient at x. Okay, remember, before we even start a first principles question, we know the answer. We know, using our quick rules, we know that the derivative of minus 2x squared plus 3x is minus 4x plus 3. That's where we've got to end up. Right, so now we're going to put in, for each of the x's, we're going to put in x plus h, and then we're going to subtract our function, just our function f of x. Okay. So it's negative. The brackets here are really, really important. I'm going to talk more about them now. But if we don't put those brackets in, we're not going to get this question right. Okay, so not for the first time today. We're squaring out a binomial. Hopefully we're getting quicker at that. Remember, when we square x plus h, we actually get x squared, which is going to multiply by negative 2. All right, I've just written those brackets in red just to emphasize how important they are. Right, now we're going to square out this binomial, x squared, but it's actually going to be negative 2 lots of x squared. Remember, we get 2xh, but that's going to multiply by negative 2. We're going to get negative 4xh. We're going to get h squared, but it's going to multiply by negative 2, negative 2h squared. Then we're going to get 3x plus 3h. And now this is where the brackets are so important, because each of those terms needs to be subtracted. So that actually becomes plus 2x squared and plus 3x. Okay, so we've made a bit of a, and in fact minus 3x at the back there. So now what happens now is that we get some cancelling happening. Anything that doesn't have an x in should cancel. Now if we left those brackets out, we wouldn't have the right signs, and we wouldn't get that cancelling happening. That 3x wouldn't be a negative 3x at the back, so there it is, it's cancelled. Everything that's left now has got an h in, so what we're going to do is we're now going to factor out the h, all right? So limit as h tends to 0, take out an h, and inside we're going to get negative 4x minus 2h plus 3, okay, over h. Because h is not 0, we can divide the top and the bottom by h. Okay, now I'm going to choose to write one more line here. You could actually go straight to the answer from here, But if you do write one more line, in other words, you write it as a single thing without a fraction, just be very aware. So I'm just going to show you here. If you wrote this, lim minus 4x minus 2h plus 3, you would actually lose a mark. You'd lose a mark for notation, and the reason you would lose a mark is because, in fact, we have to have brackets around that. That limit applies to all of that stuff. So if you write that line, that bracket needs to be there. Now on the last line, we've just got negative 4x plus 3. Differentiation by first principles is nice because you know what answer you're expecting. You know where you've got to get to, right? But just be aware of some notation stuff. The really important things to note are that the equal signs go on the left-hand side. We never put the equal signs there, all right? The next thing is that the word limit h tends to naught. That needs to be on every single line where h occurs, and it mustn't be on the last line when there's no h. And then the last thing is that if we've got that last line we must put the brackets. Now what we're going to do is we're going to do some differentiation using our rules, paying careful attention to notation. So really, really important that we don't call anything by the wrong name here. To start off with, I'm just going to use some exponent rules, and I'm going to change the square root of x cubed to x to the power 3 over 2. All right, that's an exponent idea. We're changing out of surd form into exponent form, x to the 3 over 2. Remember that the type of root goes as my denominator, and that 3 from the inside goes as the numerator. Now I'm going to split these two terms, all right? Remember, you can split fractions at the top, not at the bottom. All right, you might be wondering about the root 2 and writing it as 2 to the power of a half. Root 2 is just a number, so I'm just going to leave that as root 2. All right, notice that this is still y. I have not differentiated. In fact, I'm still not going to differentiate it. I'm just going to do a bit more simplifying. X squared over x to the 5 is x to the minus 3, and 7x to the 5 is 7x to the minus 5. Right, and as I say, I'm just going to leave that. Now, it's now what I call flat. It's got no fractions, it's got no brackets, and it's got no variables inside root signs, surd signs, okay? So now we're going to differentiate it. So we're changing its name. It's dy dx. We're going to bring that power down to the front, 3 over 2, and we're going to reduce it by 1 to a half. The next one's going to be negative x to the minus 4. Sorry, negative 3x to the minus 4, and then minus 5 times 7, minus 35x to the minus 6, and the derivative of square root of 2 is 0. There's my answer, all right? It's quite likely that they may ask us to put the answer with positive exponents, and that's kind of good practice anyway. So let's do that. I'm also changing that x to the half back to a square root. All right, that's showing off in a way, but anyway, let's do it. Minus 3 over x to the 4, minus 35 over x to the 6. All right, and there it is, nice and tidy, correctly done. Okay, part B, 4.2b, we've got a fraction, and we're going to need to get rid of this fraction. Now, the only way we're going to be able to do this is to factorize and hopefully simplify the fraction. The bottom factorizes really easily to 2 into x minus 1. What I'm hoping now is that x minus 1 is a factor on the top, because if it is, then I will get rid of my fractions. Okay, so let's do this now and see if we can work out by inspection. Clearly, I must have an x squared there to get the x cubed. At the back, I must have a plus 4 to multiply with, sorry, I must have a minus 4 to multiply with the minus 1 to give me a plus 4 on the top. Okay. Now, at the moment, if I was to multiply this out, I would get negative 1x squared. Negative 1x squared. And it would come from that times that. Now, I want negative 7x squareds. So I, in fact, need to introduce some more x squareds. And those more x squareds are going to come by putting some x's in the middle between the x squared and the minus 4. Putting some x's in there, because those x's will multiply with that x at the front to give me some more x squareds. So far I've got minus 1x squared. I want minus 7x squared, so I must put a minus 6x there. Not a minus 6x squared, a minus 6x. It will become x squareds there. Those are right now. Now let's just check, just as a safety check that our x's are correct. X's will come from multiplying numbers from the one bracket with x's by the other. That's positive 6x. Or x's from there with numbers from the right-hand bracket, and that's minus 4x. Positive 6x minus 4x, positive 2x. Great, it's correct. That's factorizing a cubic, a really important idea. Now we can divide the top and the bottom by x minus 1. Right, so we can, I don't like the word cancel, but we can divide that out. And so we've now got x squared minus 6x minus 4 all over 2. I like to, at this stage, write it completely flat. In other words, I like to write that over 2 as a half at the front, a coefficient of a half. So instead of x squared over 2, I like it as half x squared. Negative 6 over 2, negative 3x. And negative 4 over 2, negative 2. I still haven't differentiated it. Note, I'm calling it g of x, g of x, g of x. It's now what I call flat, no fractions, no brackets, no surd signs. And now I can differentiate it. And we're going to call the derivative g dashed over, or g prime, your teachers might say g prime, of x. And I get, remember that comes down and multiplies, I get 1x minus, the power reduces by 1 to 1 minus 3. And there's the answer to that question. Okay, the next question we're going to look at is the following one. All right. It says determine the equation of the tangent to this function at its largest root, its largest x-intercept. Okay, it's a cubic function. It actually goes, it looks something like this. It goes uphill first and then downhill and then uphill again. All right, and the reason I know that it does that is because of the positive value at the front. In other words, the fact that it's a positive 2 there. All right. If it was a negative, it would go downhill first. Right. Now, what the question's asking us to find is, what is the equation of the tangent at its largest x-intercept? So we're going to need to find out what are its x-intercepts. Okay. And we find x-intercepts by letting y equal 0. Right. Now, what we're going to do is we're going to look for an x-intercept by inspection, and we see that x equals 1. 1 is always a good number to try. If it doesn't work, try minus 1. X equals 1 makes that thing 0. So x minus 1 must be a factor. Now we're looking for our other factor. It's exactly the process we've just done. Let's do it again. That first term must be 2x squared to give us the 2x cubed. The back term must be positive 3 to multiply with the negative 1 to give us negative 3. And now, I look at this sort of little middle group there, the little middle pairing there. And I've got negative 2x squared. I want positive 5x squared. Now, the way I'm going to get positive 5x squared, right, is to add in 7 x's. Those 7 x's will multiply with the front x to give us 7x squared. So I'm going to put plus 7x there. It's now correct, but just as a check, let's just check where the x's themselves are going to come from. Remember, x's come from numbers with x's. Okay, so the x squareds are right. They will be right now. But as a check, the x's come from numbers with x's. There we go. There's x's there with the 3 there. That's 3 times x. Or x's from that one with numbers from this one, and that's negative 7 times x. Or 7 times negative x. Either way, we get negative 4x. It's correct. Okay, now we're going to factorize it further. Right, and this is just a quadratic, 2x and x. The signs must be the same because that's a positive at the back. And they must both, in fact, be the same as the first sign. The first sign is positive. So, in fact, both of our signs are going to be positive. And now we've got to use factors of 3, which are 3 and 1. All right, so we're going to put a 3 on the one bracket and a 1 on the other. We've just got to trial and error it and just check. The 3, in fact, must go there. The 1 must go there. And there it is. So now, in fact, I know that my roots are 1 or negative a half or negative 3. Okay. And now the biggest one is actually 1. So what the question is actually asking us for now is what's the equation of the tangent to that graph when x equals 1. Now, what we obviously know is the y value of that point is 0, right? So we don't only know the x value, we know that that point is 1, 0. What we don't know yet is the gradient, all right? How do we find a gradient? We differentiate. So there's f of x. So f dashed of x is going to be 6x squared plus 10x minus 4. Right, and now we're going to put 1 into f dashed of x to find the gradient of 1. We get 16 minus 4, we actually get 12. Right, there it is. And so we now know that the gradient m is 12. And we know that that point is 1, 0. Right, you can use y equals mx plus c. I actually prefer the y minus a y value. So y minus 0 is the gradient of 12 x minus the x value. Right, and so we end up with y equals 12x minus 12. Y equals 12x minus 12. And that's the equation of the tangent to the curve at that point. Okay, next up we're going to dive into this question. And it asks us to find values of a and b, all right? And as we've spoken about previously, often in maths when we ask to find two variables, we need to set up two equations. We know that the second derivative is 0, all right, at a point of inflection. And we know that the first derivative is 0 if the function is horizontal. So there's two bits of information embedded in that. So we know that if we put the second derivative, we know that the first derivative will be 0 and the second derivative will be 0 at that point where x equals 2. That's going to allow us to set up two equations which we can solve simultaneously. Sort of done some highlighting there. So there's going to be the equation that results from the sort of the yellow information. Let's work out the derivatives first. So the derivative is just 3x squared, the first derivative, 3x squared plus 2ax plus b. And the second derivative, obviously, 6x plus 2a. Okay, now we know that f double dashed of 2 is 0 and f dashed of 2 is 0. So when we put 2 into the first derivative, we get 12 plus 4a plus b, and we know that that equals 0. We've got one equation, it's got two variables in. We need another equation. Right, putting 2 into the second derivative, yeah, and that yellow equation comes from that yellow information that's highlighted above. Putting 2 into the second derivative, we get 12 plus 2a equals 0. Okay, and that equation we're going to kind of shade green because that comes from the sort of the green information. Okay. Right, now let's go about solving those equations simultaneously. It's actually fairly straightforward because equation number 2, as it turns out, only has one variable in it. So a equals negative 6. We sub that into the first equation, which has got a's and b's in, and we get our final answer for b of positive 12. Okay, and that's the end of that question. Right, question 4.5 says determine the values of x for which that function is concave down. Now, what we know is concave down means that the second derivative is negative, all right? Concave down like a frown. The first derivative is 3x squared plus 12x minus 5. And make sure we write what that is. It's fg dashed of x. The second derivative is going to be 6x plus 12. And we want that to be negative. Now that's a simple linear inequality, so we're going to minus 12 from both sides. 6x less than minus 12. Then we're going to divide both sides by 2, x less than minus 2. And there we have it. Okay. Right, question 4.6 deals with the whole idea of rates of change. It's an important question because it makes the important distinction between average and instantaneous rates of change. But let's first have a look. How much water is in the tank initially? Well, when T equals 0, the volume is 500. So there's 500 liters of water in the tank initially. Now, question B asks about the average rate of change. An important thing here is that average rate of change has got nothing to do with calculus, right? We are just going to use 2 points, and we're going to work out an average gradient using those 2 points. We know that at T0, there's 500 liters of water in the tank. And if we put 1 hour in, right, because we're looking for the average rate of change in the first hour, if we make T equal 1, we get another point. And that point is actually the point 1. When T is 1 hour, the volume is actually 446 liters. Right, now, it's not a straight line. The curve doesn't follow a straight line between those 2 points. I don't know what it looks like, but it's a curve. Right, what we're going to do is we're going to use those 2 points just using our standard gradient formula, change in y over change in x. Right, our y value has dropped by 56 liters. So 54 liters in 1 hour. Okay, so our rate of change is negative 54 liters per hour. So in the first hour, that was the average rate of change. Doesn't mean it was changing at that rate all the time, but the average was 54 liters per hour. And it says, did the water level increase or decrease? Well, because the rate is negative, because the rate of change is negative, it decreased. The next question, part D, asks for the instantaneous rate of change. Now, instantaneous rate of change is, we're wanting essentially an instantaneous gradient, and this is where we use calculus. So what we're going to do is we're going to differentiate V with respect to time. And that gives us an expression for the rate of change of the volume with respect to time at any given time. Okay, now we want to know when T equals 2. Right, so watch how this notation works. dV dt with a vertical line at T equals 2, and then we can put 2 in for all the times, and we get 60. Right, now that's positive 60. So that is 60 liters per hour. And then lastly, is the tank filling or emptying when T equals 2? Well, it's clearly filling because it's positive 60. There's an uphill slope, an uphill gradient. Okay. Over there, downhill gradient. Okay, let's move on to the next question. And this is an interesting question because it gives us a whole lot of information and asks us to draw a graph. Right, let's just have a look at what we've got. The first thing is that we've got f of 0 equals 5. Right, that means that when x is 0, y is 5. That suggests that 5 is the y-intercept of our function. We're then told that f of 4 and f of negative 3 are 0. Right, those are x-intercepts. They are often called roots. They're also called zeros, right? They're zeros because they make the function 0. So positive 4 and negative 3. Those are x-intercepts. Okay, trying to sort of color code this, we found the y-intercept, the blue point underlined in blue, the x-intercepts in red. All right, and now let's have a look at what this is saying. It's saying that the graph is concave down. All right, the second derivative is negative when x is less than 2. Right, now what that means is the second derivative is negative. It means that the graph is concave down. It's kind of like a frown, okay, as opposed to like a cup. Concave down, like a frown, and concave up, like a cup. Okay. Graphs are concave down when the second derivative is negative. And they are concave up when the second derivative is positive. Right, so we know that this particular graph is concave down. It does something like that until 2. After 2, it'll be concave up. The last piece of information is that the graph actually turns at 0 and at 4. Right, so there are turning points. The gradient is 0 at 0 and at 4. Right, so the graph does something like that. Okay, and we know that it's concave down at 0. Right, so it definitely is a maximum turning point. So the final answer is something like that. Right, and somewhere over there at 2, we have a point of inflection. That is where the graph changes from being concave down to concave up. Okay, the concavity changes. Right, we are heading towards the end. I think we've got 1 or 2 more questions to do. In fact, just 1 more question to do. Right, here we've got a right-angled triangle. A is at the origin, and B is on this parabola, this concave down parabola. Okay, and a triangle is formed, and we want to make sure that that triangle is as big as possible. Now, the question says to us that if that point is C, what's the y-coordinate of that point? And we've already come across this in this paper. It's just negative c squared plus 4 because it lies on the parabola. Right, the next question is what's the area of this triangle? Right, and so I'm going to answer this over here just so we've got the picture. But the area is going to be half the base times the height. Right, what we didn't fill in yet is the fact that C is the point C0. Okay, C is the point C0. All right, so the base is clearly C. And the height is just the y value of that point, of point B. It's negative c squared plus 4. Okay, and so if we multiply that out, we get negative half c cubed plus 2c. Right, and that's the answer to part A. Part B then says, hence find the maximum area that's possible. Right, now if we want to maximize an expression, we need to differentiate it and equate the derivative to 0. So let's differentiate that. We get dA dc is negative 3 over 2, negative 1.5 c squared plus 2. And we want that to equal 0. So it should be negative 1.5 c squared. So 2, in fact, equals 1.5 c squared. Sorry, that should be c squared. I think we're going to pick up on that. There we go. C squared. Right, complete mess. Let's just fix that. So we should get 2 equals 1.5 c squared. Sorry. One and a half c squared is minus 2. And so c squared is in fact 2 over 1.5. And then we can just square root c to get our answer. Now that answer, right, for c is not the answer to the question, because the question actually asks, and notice it could be a positive or a negative. If it's negative, it's just on the other side of the y-axis. It's just a reflection. So we're only going to worry about the positive value, and it comes out to about 1.155. Right, that's not the answer that we're looking for. We're looking for the maximum area of the rectangle. So what we're going to do now is we're going to pop that into the expression for A, and we get a final answer of about 1.54 units squared. That's to the end of this paper. I hope it was useful.